welcome Preethi, Srinivasan, and Shruti Dhavalikar for their talk on big models, small tweaks. Take it away. Thank you.
Hey, hi. This is Shruti and I'm Preethi. We are working on vision and language models at Sahaj. Today we'll be talking about why and how parameter efficient fine tuning works, and specific. Yeah. Specifically, we'll be talking about this algorithm called LoRA, which expands to low rank adaptation. We'll talk about the details of how it works, inner workings, etc. Yeah.
So, hello everyone. Thank you so much for coming over here and showing the patience of sitting through the conversation. In the talk, first we'll walk you through the concept of LoRa and in general why you have to sit through this half an hour presentation. Then later we'll dive into, rather, if we make sense, then we'll dive into fine tuning exercises, the details about fine tuning. Then later we'll understand LoRa from its fundamentals from scratch. Then we'll set up a toy stage where we'll try to implement LoRa. Then we'll perform fine tuning using LoRa. And then once our model is ready, we'll try to share the model across platforms. We'll share some techniques to do that. And last, we'll discuss limitations for LoRa, where LoRa can be used, where LoRa should not be used. So, let's jump into the concept. On the screen, on the right side, you can see some names. If you are not so tired, please raise your hand if you are familiar with some of the names over there. Amazing. Nice. So that emphasizes the fact that we live in the world of large models, maybe large language models, large vision models, multimodal, whatever. But then we live in the world of large models. Now, let's have a look at, since we are talking about large language models, maybe let's have a look at the size of these models. So before this ChatGPT era, there was GPT-2 model, which was consisting of 1.5 billion parameters. Then later Llama came, many other model came, the classic 3.5 turbo is 175 billion parameters. Now we are with 4, GPT-4, O1, whatnot, which is coming out to be 1.8 trillion parameters. The point which I am trying to show over here is, when we say large models, it comes, or rather, the increase happens from 1.5 billion parameters to 1.8 trillion parameters. And that change happened maybe within 1.5 to 2 years approximately. So every day, the size of the models is increasing enormously, and we have to sort of comply to that. Now, let's understand when we say the models are huge, that is not number of billion parameters, right? That is not the measure which we use day in, day out to measure the model size. We need to have like a measure which will give us the look and feels of size of this model, right? Otherwise it becomes this case, which we really do not want. So, I found like this interesting chart on the internet which says that, so for people who are not able to read, on the left side we have a column which says that number of parameters in billions, and if you load it into a particular data type, then what is the amount of GB of RAM that you will require to load it into the memory. So, as you can see from this chart that if your number of billion parameters are increasing, the memory requirements are increasing. They require large amount of memory to just load it into, to just load it and make it work. Now, let's assume all of us, we are rich and we have that much of memory available in our pockets. Now, still can we use these LLMs as it is for a particular business case? Let's take an example. So a person over here is chatting with some airline's conversational assistant, and the person says that, where is my flight right now? The assistant says that your flight is delayed because of some weather conditions. The person is still trying to cope up with the drama. And now the question comes where the person says that what is the impact of weather on ATC? For the people who are behind, this is the zoomed in version. So here ATC means air traffic control. Of course, we know that from the context of the chat. But here the LLM got easily confused that ATC acronym with add the counter. Why? Because it is trained on enormous internet data. Now internet data will have everything, add the counter also and air traffic control also. Now how can you make an LLM understand the context of the business or the domain in which it is operational? One simple way is to give it a prompt. But prompts are not always exhaustive. You sort of try to tweak in one edge case over there and you can miss out other. By any prompt, you cannot always make 100% sure that it will serve 8 billion population. That is not exhaustive. Plus, if your conversation length grows, then it may deviate from the prompt, it will hallucinate, whatnot. So, fine tuning is still not off the chart. We have to fine tune the model to make it functional into a particular domain. Now, so let's dive deep into fine tuning. Now that we have understood why we have to do fine tuning, consider this as a model. What is a model? Model is number of layers. And what is a layer? Layer is just matrix of numbers. There are just numbers fed into the model which we call parameters, and that is what we were measuring. Now when we fine tune a model, we decide to change or alter or train as many numbers present in all the layers, or we can choose to train only some layers of the model. Conventionally, we try to choose the last layer because that is the layer we can have after tweaking with respect to the fine-tuning task which we are performing. The initial layers are mostly dedicated to understand the fundamental information about the data, so mostly we need not to tweak them. Now, let's apply this conventional fine-tuning in terms of the large model which we were talking. Example is, in Llama 3 8 billion model, there are 32 layers. If we decide to train the last layer, which is again each layer over there consists of 218 million parameters. Now let's try to have understanding of what does that contribute to in terms of resources. If you want to load just this model, 8 billion model, which was the smallest over there, it will take 8 into 10 raised to 9 into 4 bytes per parameter, that much of memory just to load the model. And while training that last layer, you will require 218 into 10 raised to 6 into byte size into 3, that is 4 gradients and moments which will require to store during the training process. So that is really expensive. Can we make it a little more efficient? Because not everybody will have pockets full, our assumption. So can we make it a little more efficient? Now, instead of doing the conventional fine tuning, we will try to offer parameter efficient fine tuning. As the name says, we are going to optimize on number of parameters which we will train. In the PEPT, we are going to go for adapter based fine tuning. Now, adapter based fine tuning will actually allow you to introduce some extra parameters as adapters, as we said, so that we can actually control the number of parameters which we are newly introducing, and hence controlling the parameters or trainable parameters is going to eventually cause the reduction in the memory requirement. So that is how it is going to help us in the resource reduction. Now, let's understand some fundamentals about PEPT before getting into the main topic. So, the parameters which we are newly introducing for the fine-tuning process, they are called as adapters, and the model or the base model into which we are introducing these adapters, the layers are called as adoptees. Now, there are two important conditions for the adapters to satisfy. One is they should be small in size. Now, why? If they are as big as the main model layers, then we are losing out the whole point of saving resources, of course. And then, since we are introducing new weights, we have to initialize them, right? The deep learning logic. So, if we are initializing them, we have to make sure that they will not disrupt our inference performance or pre-training performance. Now, how to do that? That is something Preethi will answer. So wait out till that point. We'll go to LoRA first. In LoRA, so LoRA is low rank adaptation. In low rank adaptation, we insert new low rank metric as adapters into our base model. If you can see, that is our pre-training model layer. We have an orange layer, which is like introduction of new adapter layer, and how much of parameters we are newly introducing, that is directly controlled by the parameter called as R. As we discussed right now, two things. One is it should be small in size. The smaller size of R is like smaller number of parameters you are introducing, and hence you are saving out on memory. Second, initialization of this layers or matrices is totally possible. How to do that? That's something Preethi will explain to you. But instead of just jumping on large models directly, we will implement LoRA first on a simple multi-layer perceptron network and try to understand what are the changes which are happening when we apply LoRA for a fine-tuning task. Still with me, everyone? Cool. Okay. Preethi, now the stage is yours. Hey, hi. So, okay, let's.
Okay, so let's try to understand the how and the why of LoRa by implementing it on a small model. So to do that, let's set a stage first. So let's come up with a toy dataset, toy pre-training task, small model. We'll pick an MLP or simple model. We'll come up with a toy fine-tuning task, and then train the model with LoRa on the small model that we just spoke about on the fine-tuning task. So the reason this is basically to dissecting the large language model is much harder. To get into the details is much harder than getting into the layers of MLP. So basically, the architecture nuances is more visible with LoRa on an MLP than in the large one. That's the whole point of this exercise. So first step, let's create the toy dataset. So let's pick 1,000 data samples. Each of the sample is a vector of 20 elements. So the sign of sum of these elements, if it's greater than 0, well, let's label it 1. It's less than or equal to 0, let's label it 0. So this is our binary classification task. So now we have our training data and the evaluation data ready. So the next step is to create a small model. Let's create a 3-layered MLP. Most of you must be aware of multi-layer perceptron. So we'll create a 3-layer fully connected layers. So fully connected layers is nothing but all the neurons in the input set are connected with all the neurons in the output set. So for the connections, all of these connections are the weights that we are talking about, the weights / parameters, whatever we're talking about. So there are 3 fully connected layers in this model. So fully connected layers is also referred to as linear, is also referred to as dense, same name, same thing, different name, sorry. So we have 3 layers here, and apart from that there are also activation layers. So now let's print the number of trainable parameters in our network. The total number of parameters, if you were to calculate, will be around 4.4 lakhs. All of them are trainable, right? So now let's do the pre-training, So as part of pre-training, we have to first set the configuration. We'll have to set what the learning rate is, what the batch size is, etc. And then let's set up the training code, and then let's train the data, as in train the model on the given binary classification task. We can see that the loss is decreasing steadily, which means there is some signal in the data. That is why the loss is decreasing. So another point is that pre-training typically, whatever people refer to as pre-training with respect to large language models, the pre-training is done on internet load of data. But here, since we are trying to replicate the whole scene on a smaller stage, let's call this exercise pre-training. All right. So now next job is to fine-tune with the LoRa. So objective here, let's make the objective very clear. The objective of this experiment is to test for the parameter efficiency. We discussed that LoRa is one of the PEF techniques, parameter efficient techniques, adapter-based PEF techniques. So let's test for that parameter efficiency. How is LoRa parameter efficient is what we want to understand, right? The stage is not ideal to see the performance of LoRa on a model, because the performance of LoRa is more pronounced on large language models with very well-defined downstreaming tasks, which most of you are familiar with. So that's not what we're doing here. So PEF is a library developed by Hugging Face, which helps us to implement LoRa. So the next question is, Shruti already established that adapters are these few extra parameters or few extra layers that you're injecting into your base model. Now, obvious next questions are, where do you inject them? How do you inject them? How are you going to plug them in the base model? These questions. Just try to answer those questions. So, where to inject adapters? So, if your base model has, say, 10 layers, you want to pick some of those layers and then inject your adapters, okay? And how will you choose those layers? That's a very strategic choice. Like, you can either go wrong into two counts, right? Two extremes. One, either you can choose wrong layers such that it will cause catastrophic forgetting. That is, you're making the base model lose what it's learned, or you're going the other way around and it's not impactful at all. Like, for instance, if you choose to adapt a normalization layer, you may not really see the model learned for the fine tuning. It's not impactful at all. So strategically choosing is very important. So the paper dedicates the entire section to empirically study which layers have most impactful learning on a fine-tuning task, the LoRa paper. So let's first print the names of the modules in the base model. So we have sequence 0, sequence 1, 2, 3, 4, and 5, of which 3 of them are activation functions, activation layers. So these activation layers are not learned, so therefore you don't need to adapt them. So we have 3 options left, sequence 0, 2, and sequence 0, sequence 2, and sequence 4. Let's pick 2 of them, sequence 0 and sequence 2. That's what we want to adapt in our exercise, right? Now the next question is how to inject these adapters. Now we have chosen 2 of them. Now how do you do that? So let's go back to slides. Option 1 is doing them sequentially, okay? So if these blue blocks are your base model layers, sequence 0, sequence 2, and sequence 4, and A0 and A2 are adapters. respectively. A0 is the adapter for sequence 0, A2 is the adapter for sequence 2. So one option is to do it sequentially. Now there are two disadvantages with this design. One is that GPU memory is not fully utilized because GPUs are optimized for parallel processing. So when it's looking at this block, it's looking at a really small, doing very few computations, right? So that's one thing. Second thing, the design itself, the very nature of the design means the forward pass is going to take longer. Sequential design means it's going to take longer. So forward pass is taking longer, then training and inference time is also going to take longer, right? Now LoRa proposed doing this in parallel. So you have sequence 0, will put the adapters in parallel so that a copy of the input goes into the base model layer, a copy of the input goes into your adapter layers. Okay, let's look at the design in a lot more detail little later. So another thing that LoRa proposed is we looked at these adapter matrix. Adapter matrix as adapter layer is basically just matrix of numbers, right? So adapter matrix, although they are small, Shruti already said that it is smaller compared to the base model layers. Otherwise, there's no point of this whole parameter efficiency in the first place itself. Although they are small, they are full rank matrices. They are not. So the authors of LoRa proposed, why don't we decompose this into two small low rank matrices? Like if your adapter matrix is a size 200 cross 2000, which is basically carrying about 4 lakh parameters, you decompose them into two small low rank matrices. You give a rank, you choose a rank, it's a hyperparameter. Let's say if your R is equal to 3, then your LoRa A is 200 cross 3 and LoRa B is 3 cross 2000. So essentially you're carrying 600 and 6000 parameters, about 6600 parameters in total. Now where is this inspiration coming from? What is the idea behind LoRa? A small recap of SVD, singular value decomposition. Suppose if this matrix A is your data. This is your data. Like there are some 4 lakh parameters. This is your data that you want to transmit from your source to destination via some bus. Instead of sending all the 4 lakh parameters, one way is to send these two smaller matrices called B and C. If there is a technique called SVD, which will, you give an A and you tell a rank, it will decompose the A into two smaller matrices called B and C of the size 200 cross 3 and 3 cross 2000. Okay. Now you are carrying only 6600 parameters. You go to the destination, you rebuild the full dimension matrix, which is because if you multiply 200 cross 3 and 3 cross 2000, you get the 200 cross 2000 back. But the value, the matrix won't be exactly the same. It will be an approximate value. So if you can discount for a little bit of accuracy or loss, then this is good to go because you are basically solving for a lot of data redundancy. This is standard data compression algorithm that is used in most ML techniques, right? So here SVD identifies this B and C given a A and a R. Now what LoRa proposed is we learn this B and C. You initialize the B and C some way and you learn this B and C matrices, B and C layers, whatever you call it, for a specific fine-tuning task that you want to choose. So this is the overall block diagram that you're seeing on the left. The input, a copy of input is going into this red block. This is red in color because we already discussed that base model layers are frozen during the fine-tuning process. Only the adapters are being modified. So one copy is going into the sequence 0. Another copy is going to LoRa A. I mean, each base model layer is decomposed into two small matrices, right? One is LoRa A and one is LoRa B, corresponding to sequence 0. So one copy is going to sequence 0, another copy is going to LoRa A. So the outputs of the LoRa A comes out, then it goes into LoRa B, and then comes out of LoRa B. Now note that the dimension of the output that's coming out of sequence 0 and the dimension of output that's coming out of LoRa B has to be same. Only then you can do element-wise addition. I'm just trying to emphasize the design choices of the paper. Okay, so you do element-wise multiplication, send a copy again to sequence 2 and send a copy again to the adapter of the sequence 2, continue therefore. Sequence 4, we chose to not have the adapter here in this particular example, so this is how it is. So matrix there are many ways to represent the matrix. This is one way. Some people prefer to represent it as a set of arrows. So this is a detailed architecture for people who are interested in looking at detailed architecture. So let's look at how will the forward pass look like. So your X is the input. It's going via sequence 0, getting out sequence. It's coming out of sequence 0 as sequence 0 underscore out. Which means I am here, right? And then the same input is going into sequence 0 of LoRa A, which is the smaller matrix, first smaller matrix. It's coming out as LoRa A out, and then it's going into LoRa B out, and then to the second smaller matrix and coming out as LoRa B out. Basically, when it is going, it means that it's getting multiplied. LoRa A and LoRa B gets multiplied, right? So here we are here. and this right now in this forward pass we are over here, right? Now the next part is to do element-wise addition with a factor of alpha. So alpha is going to decide how much your adapters are going to influence the whole fine-tuning process, right? And then the entire forward pass looks like this. You repeat this for sequence 2 and so on, right? So whatever we saw now, we'll try to implement on the code and see. So first we said we'll have to configure the LoRa parameters, as in LoRa hyperparameters. We'll have to come up with a rank R. You can empirically do a lot of experiments and decide for your task, for your model, which R makes sense, and so on. And then the target modules you want to adapt are sequence.0 and sequence.2. These are the two we chose to do. So now we use the PEFT libraries get PEFT model. This PEFT model is nothing but the expanded network. Now it has base model. It also has the LoRa adapters. Exactly the way we saw the architecture before. If you were to do a graphical representation, that's what it would look like. This is, I don't know, code representation. If you were to look on the code, this is how it will look. So there is sequence 0, and there are LoRa A and LoRa B corresponding to sequence 0. There is ReLU, and then there is, we also adapted sequence 4. So there is also LoRa A and LoRa B corresponding to the next one. And the last layer we did not adapt, so it remains as it is. You see that there are no LoRa adapters here. So the next question is how to initialize them. We spoke about initializing of adapters is important because you should not cause training instability. So the two important things to note here is there are two extreme choices, right? One is zero initialization. Initialize all the neurons to all the weights that you have to 0, right? Now all of them will learn the same thing. They are not going to, in each iteration, all the neurons are going to learn the same thing. They are not going to learn different stuff. Each neuron is supposed, unless they learn different stuff, it cannot understand complex information, right? So the notion is called symmetry breaking. The symmetry has to break. One of the key aspects of having a good initialization algorithm is to break the symmetry. And the second extreme choice is to do random initialization. Then the training will go bazooka, like it can completely go destabilize. So LoRa gets the best of the two worlds. It initializes the first smaller LoRa A to 0 and LoRa B to random Gaussian noise. So why this choice? Because the product of LoRa and LoRa B in the first iteration is 0. So in the first iteration of your fine tuning, the adapters are not contributing at all. So the training is smoother. It will slowly, the neurons will start learning because of the random noise that is there in one of the matrices, the symmetry will break and then the learning happens slowly. Right? Now how to prove that this initialization works? Let's say you have the PEFT model now, that is the expanded network which we saw just now. And you pick the pre-training task, as in pre-training data and task, and you run it. The first epoch of this has to resemble the last, like if we had run the pre-training for 20 epochs, the first epoch of this PEFT model or this training exercise has to resemble the 21st epoch of your pre-training task. It should look like that. It shouldn't, which means I'm saying that the training has to be very stable, it has to be very smooth. The loss has to reduce very smooth. Adapters should not have any role during the fine-tuning in the first epoch. So that's what is happening. We see that a very small reduction compared to the epoch 20 of the pre-training. The next part is fine-tuning on the downstream task. Now we have to come up with a downstream task. The downstream task has to be relevant, but it should not be identical, right? Downstream task meaning fine-tuning task. Now let's pick. Typically, the fine-tuning task will have much fewer samples than the pre-training task. Like if I were to escalate this example to LLMs, you will train the LLM, pre-train the LLM with infinite amount of data, but if you fine-tune it, you're only going to fine-tune it on your domain-specific case studies or like contracts or something like that, which will be much fewer. So let's take 500 samples. Each sample is a vector of 20 elements. Some of these 20 elements, if it's greater than 10, you label it 1. Less than or equal to 10, then you label it 0. This is our binary classification task. It's relevant, but it's not the same thing. So you see that the loss is decreasing, which means the fine-tuning is happening, which means the adapters are learning with respect to the fine-tuning task that we have given. Now let's verify if the LoRa is applied correctly. One of the things that we mentioned is the base model layers are frozen. They are not trained they are not modified during the fine-tuning process. So let's print the base model layers, names of the base model layers and names of the PEFT model layers. And if we actually compare, we'll see that all of them are equal, as in the base model layers have not changed. This is just a sanity check, right? And one thing to note is that the adapters that you have introduced into the base model, the green color matrices that we saw, those are the only extra parameters that are going to be fine-tuned. So those are some 12,600 parameters that you have introduced into your base model. So the expanded network has now become, instead of 4.4, now it has become 4.5 lakhs, obviously, because 12,000 extra parameters are added. But only the 12,000 parameters are trainable. So only 2.7% of your entire network is trainable. This is where the parameter efficiency comes into picture, right? So, yeah. The next part that we will look at is, for the interest of time, I'll skip. We will have this collab notebook in the end, so you can check all the other sections. So merging the adapters. This is another design choice of the algorithm, the LoRA algorithm. Your network has expanded, right? If you don't have, let's say for some reason, although the adapters are significantly smaller in size compared to base model, you need both of them to sit together, right? Like suppose if you don't have enough space to accommodate your adapters, then the design of LoRa helps you, because if you multiply the matrices back, the original dimension of the matrices, you get back the original dimension, right? Which allows you for doing element-wise addition, right? So you can actually club them. So your 4.5 lakhs becomes again 4.4 lakhs, right? So that's the design choice of adapters. The next part that we will be looking into is sharing this in the hub. Basically, so one of the key things is, as we discussed before, you can have one adapter trained for one specific downstreaming task. Suppose if you have 10 adapters, you can just have these 10 small adapters for 10 downstreaming tasks. You don't have to save the entire model. Just save these adapters and you're good to go. Pull the base model, whichever fine-tuning task you want, pull the adapter related to that, plug it in using the configuration, do the inference. You're done. You don't have to save the entire model. So we'll see that. We'll try to upload the adapter and compare the size, which we spoke from the beginning, which Shruti also mentioned in the beginning. Your adapters are basically, that we chose to do in this experiment, is just about 51 kb, right? Your original, the base model, the MLP model, is the size 17 MB. This difference, relative difference, will be way more pronounced in case of large language models. Like when you're working with large models, then the base model size and the adapter sizes will be hugely different, right? Now you're loading the model from the adapter. So the technique is the same thing. You bring the base model, you bring the relevant adapter that you want, plug it in, and use them, right? Now when you bring the base model and the adapter, and you using the config, when you plug it in, you're using basically the expanded network. So you're having about 4.5 lakh parameters in your machine right now. Now you can merge them together, make them 4.4 as we just discussed before, and use them for inference. So again, a sanity check. This particular model is already sitting in your machine, and I have just downloaded one from the Hugging Face. I just want to see if they're going to produce the same outputs. Yes, they do. The tool is for that. Yeah, there are some other extra stuff which you can look into, how we calculated the amplification factor and stuff. So this is the sharing the model through Hugging Face Hub. This is your base model, which is frozen. This is your green adapter, which is fine-tuned. This adapter is what you're interested in. Plug it out, put them in the hub. So these 7 yellow blobs are for 7 different downstreaming tasks. Small blobs and one base model. That's it. Right? Let's look at the performance. We already discussed that it's compute efficient, which means you are only fine-tuning few parameters. So you need the training process itself, for every parameter you will need 4x space, right, to save the gradients, moments, etc. So you need much, because you're dealing only with fewer parameters, it's compute efficient. Storage efficient, because Shruti spoke about one example where she said Llama 8 billion, 3.18 billion. If you were to do one layer of fine-tuning like conventionally, you would probably be fine-tuning about 218 million parameters. That's prohibitively expensive if you were to do it. But if you were to apply LoRa and do it, across the entire network, 5 million parameters, and you're good to go. 5 million parameters because I chose a rank is equal to 2, right? Next thing is amplification factor. This is a metric which they discussed in the paper. This metric is to measure how well your model has learned for the fine-tuning tasks. They will do feature comparison, magnitude of feature comparison between base model and the adapters. You can get into details. There's Collab notebook and places to learn that from. So yeah, that's what amplification factor measures. And they noticed, or they empirically found that amplification factor as less as when rank is equal to 2 was giving much higher amplification factor, that is the learning was better compared to when rank is equal to 64. And specific examples in papers also like GPT-3 with 175 billion parameters.
Sorry about having to cut you off. We are at time right now.
Oh, okay.
So the keynote is starting in 10 minutes. Preethi will share her slides online and we'll share it with you. She'll hopefully be around during the conference today and tomorrow. Yeah, so you can catch her and discuss anything that you have with her. She'll be happy to reply. But right now we encourage you to go to the auditorium 1 where the final keynote is happening. And we'll see you there. Thank you.
This talk is based on 2 blogs that I wrote on exploring LoRA, those references to 2 blogs, and the third blog on the theoretical inspiration for the algorithm. All of them are there. The collab notebook is also there. You can have a look at it.